Hello and welcome to today's lesson in refraction, which is part of the waves topic in GCSE Combined Science Physics. So in today's lesson we're going to try to understand the process of refraction. So if we're successful and we learn today, we can detail the process of refraction, understand refraction is due to the difference in velocity of the waves in different substances, and construct ray diagrams and wavefront diagrams to illustrate the refraction of a wave at a boundary between two different media, which links into the following part of the GCSE Combined Science topic, Properties of Electromagnetic Waves 1 in the Physics section of the course, which if you note is a higher tier only specification skill point. So all waves carry out three different processes when they hit a material. They can carry out reflection, which is where a wave hits a surface and bounces back. They can carry out refraction, where a wave goes through a surface and changes speed and direction, and they can carry out absorption, where the wave's energy is deposited into the object. Now, refraction is an example of transmission. Transmission is when a wave moves through a material, but refraction is when a wave changes speed and direction when it transmits through a material. So refraction is a type of transmission. Now, refraction of a wave occurs when a wave travels into a new medium. So for example, air into glass. Now let's consider this particular situation. Now there's an incident ray, which is the incoming ray to the new material, and the light entering the new material can form what we call an incident angle, because when the wave moves through a new material we call this transmission. Now at this point, partial reflection can also happen at the same time as the transmission process. But remember, light hits a surface at the normal. Now the normal is an imaginary line drawn down to help us understand the process of refraction. Now this allows us to measure the angle of incidence. Now the angle of incidence is from the ray to the normal point, which we've drawn on our diagram. Now when a wave hits a new substance or medium, it will change speed. Now if the medium is denser, it will slow down, and as a result it will change the direction of the wave, and we call this process of changing speed and therefore direction of the wave refraction. So we will say the transmitted wave has been refracted. Now just to note, because glass is denser than air, this makes the wave slow down, this makes the wave change direction, this has given refraction. So if the wave was traveling from air into glass, therefore it could possibly speed up. So if it was speed up, it would move away from the normal. But if it's slowing down, it will move closer to the normal. Now we can measure how much the wave has changed direction by measuring the angle of refraction. Now you can note the angle of refraction is from the normal, which is drawn as the dashed line on our diagram, to the refracted ray on the other side of the block. Now, in refraction, it's important to note that the speed of the wave is changed. Now, this happens because the wavelength of the wave is altered, and it's very important to note that the frequency of the wave doesn't change at any point in a wave's journey. Now, we can represent our refraction in a ray diagram as shown on the screen currently, or we can also represent refraction in something called a wavefront diagram. Now, a wavefront diagram is where you would draw wavefronts on your rays. Now, the wavefront represents the front of one wave travelling, and it's found perpendicular to the direction in which the wave travels in. Now you can see this is an example of a wavefront diagram. Now in this particular example of refraction, we know light is slowing down. Now we know that for three reasons. Number one, it's going into a denser medium, so it must be slowing down. Number two, the refracted ray is closer to the normal than the incident ray, indicating it must be slowing down. And finally, the wavefronts on the wavefront diagram are closer together, so that tells us that it must be slowing down. Now the distance between two wavefronts is the wavelength. So if the wavefronts are closer together, this tells us that the wavelength is smaller, so the speed is slower, but the frequency has remained constant. Now just to note, by the way, the angle of refraction is the angle from the normal to the refracted ray, not the normal to the outgoing ray. It's a common mistake people make. Now just to clarify an idea, you only observe refraction when light or any wave hits a new medium at an angle. You do not observe refraction when light travels parallel or perpendicular into a new medium. Now why is this? To understand this idea of refraction and why this bending effect occurs, occurs, let's think about refraction as the marching of soldiers. Now, as soldiers walk onto sand from grass, the soldiers that would walk onto the sand would slow down, but because they're moving at an angle, certain soldiers in the row are going to walk onto the sand and slow down before the other soldiers, so that will cause the line to bend because some soldiers have slowed down whilst other soldiers are remaining at the same speed, which causes this bending or skidding effect for your soldiers, which will be the same thing for light. So let's look at this particular diagram. As the new wavefront in this situation hits the new material at an angle, some of the wavefront, the parts that have encountered the new material, will slow down because they're now in a denser medium, whilst the rest of the wave has not yet entered the new material and has not yet slowed down. So this means that there's a difference in wave speed across the wave. So what this will do is this causes the wave to bend in refraction. Now, if the wave is going to hit it dead on, so it's going to hit at the new material at a zero angle, all the wave will hit the new material at once. So yes, the waves will change speed because they're moving into a denser medium, which we can see because the wavefronts are closer together, but because they're all changing speed at the same time, refraction will not occur. This bending effect does not take place. So this occurs as all of the wavefront changes speed at the same time as it encounters the new material at the same time. So this means no bending of the ray will occur. So let's just recap what we've learned so far. When a wave goes from one material to another, this is called transmission. If it changes direction during this is called refraction. This is because waves travel at different speeds in different materials. Now, the waves change speed as they change their wavelength because their frequency remains the same. But waves change direction and refract when moving between materials when some of the wave changes speed before the rest of the wave, which occurs when a wave hits a new material at an angle. So when a wave travels to a denser medium, the angle of refraction is smaller than the angle of incidence. This is because the wave slows down, the wavelength has decreased. Now, when a wave travels into a lighter medium, the angle of refraction is larger than the angle of incidence. This is because the wave speeds up, the wavelength has increased. So we can look at this particular example in an investigation by measuring the angle of incidence and the angle of refraction. So in this investigation, you would want to find the relationship between the angle of refraction and the angle of incidence for a wave hitting a new medium. So what you would need is a rectangular glass block, a refraction drawing grid, a light ray box and slit, and a protractor and a ruler. So the first thing you do is you retrieve a power pack, you set it to 12 volts DC, you then place a rectangular glass block at the center of your refraction grid or just a piece of paper, making sure the transparent side is facing upwards so you can take measurements later. You then use a sharp pencil to draw an outline of the block on paper, ensuring the block doesn't move when you carry this out. You then draw a normal as a dashed line because it's not there really, it's a construction or an imaginary line. You then can draw your normal all the way through the block at a particular point where you want your light to hit the block. You would then use a protractor and find the correct angles of incidence, so 10 degrees, 20, 30, 40, 50, 60, 70, 80. Now you would want to measure it from the normal. You would then draw in and label your line with your particular angle. You then do that for the different angles that you would want to use for your angles of incidence. You then place the block on the paper on its outline, ensuring the block is placed exactly back on its outline. You connect a ray box to the power pack, ensuring the ray box is connected to the DC setting of the power pack. You will then place a slit on the light ray box to ensure there's only one ray of light being used, so we can do our ray diagram. So this gives a long thin line to show the wave. The thinner the line, the more accurate the results you will gain. You will then use the light ray box as shown to direct the light ray at along the line you want to measure so it enters the block correctly, making sure the transparent side is facing upwards. You then place 3 crosses on the light ray coming out. You then join up those 3 crosses with a straight line, and then what you do is you then connect that with a straight line from the normal where it enters to where it leaves the block, because electromagnetic waves always travel in straight lines. You can then measure the angle of refraction, which is from the normal to the refracted ray as shown on the diagram. So you would use a protractor and you would record your angle of refraction, and you repeat this experiment for all the different incident rays of 10, 20, 30, 40, 50, 60, 70, 80 degrees. Now you might find it will be useful if you drew those in different colours to allow you to easily see the different angles. You then fill in your results with the observations in your results table, recording your angles of refraction in degrees. You then draw a graph of your experimental results, placing the angle of refraction on the y-axis and the angle of incidence on the x-axis, and you label your axes with a heading and a unit, and then you will place your angle of best fit, your line of best fit on your graph. So let's just recap what we've learned in today's lesson. Different substances may absorb, transmit, refract or reflect electromagnetic waves in ways that varies with their wavelengths. Some effects, for example refraction, are due to a difference in the velocity of waves in different substances. You should be able to construct ray diagrams to illustrate the refraction of a wave, and you should be able to use wavefront diagrams to explain refraction in terms of the change of speed that happens when a wave travels from one medium to a different medium. So if we've been successful and we've learned in today's lesson, we can detail the process of refraction. We understand refraction is due to the difference in velocity of the waves in different substances, and we can construct ray diagrams and wavefront diagrams to illustrate the refraction of a wave at the boundary between two different media. I hope you've enjoyed today's lesson looking at refraction in the waves topic of GCSE Combined Science Physics. Thank you very much for listening and have a lovely day.